Hey everyone, this is Doug. Today I'm just going to walk you through how to get Xfoil results in a useful format so they can be used in MachUp. I've had several people request this, and so I'm finally getting around to making a movie about it to kind of walk you through the process. So I'm just going to start from our home page, the arrow.go.usu.edu page. From there you can go up to Open Tools, go to our Google Drive, and on this Google Drive, we have a bunch of different spreadsheets and things. Here's the Airfoil coefficient calculator.xls. You notice that that's a Excel spreadsheet. The others are Google spreadsheets, but there's something in Excel. It's got a solver that allows us to get more accurate representation of this data. So this actually has to be run in Excel. So I'm going to download it from off of the drive, and here it shows up in my downloads folder. So I'll just open it up. Now, I'm working on a Mac. I'll talk about the differences here in just a second for Windows. But so here you can see it popped up in Excel, and within this spreadsheet it has instructions of how to do this, and so hopefully those are clear enough that you won't need to refer back to this video. But as a first time through, it's helpful to have someone to walk you through it. So I'll just walk you through it here. The data that you get out of Xfoil, basically in Xfoil you're going to put in an angle of attack. It will tell you the lift coefficient, the moment coefficient, and the drag coefficient. And so this is the raw data block here that you'll be getting from Excel. That's your raw data. And if you need to add more lines, if you have a bigger data set, if you run these in finer intervals or over a larger range, you can click here in the margin, drag down, and then right click and say insert here, and just insert a bunch more lines. Now the trick here is if you're going to insert more lines, all of these guys over here that are the computation for each of these lines, you need to highlight that and drag down. You notice that my cursor turns into a black plus when I go over that square there at the corner. If you drag that down over the new lines that you've added, if I add in more data over here, I'm going to highlight this, click here in this corner, drag down, and that will copy all of the computations that are happening up here on this set of data. Then we'll be doing similar computations on the new data that we added here from these lines that we've added. So anyway, once you have your data set in there, so we're just going to run with this data set that's already built into the spreadsheet. This data I believe came from Xfoil. I'm pretty sure it did, and so we'll just walk through it. So you'll drop your data in this set here. Now these first two columns are trying to estimate some equation, some way to represent the lift as a function of angle of attack. So basically what MachUp needs is a zero lift angle of attack and a lift slope. So these two numbers, Excel hasn't solved for these yet, and so when you get this, these are obviously not going to match your data. But these are the only two numbers that are needed by MachUp in order to predict what your lift is at any angle of attack, basically, below stall. So so down here, if we scroll down, we've got a plot of the lift coefficient, and the black dots are the actual data, and if you click on them, you can see that that's what it's plotting up here, angle of attack and lift coefficient. So the black dots are the data, and then the blue line is actually plotting this column as a function of angle of attack. Now this column is the lift as predicted from an equation. That's why it's got the underscore EQ there. So this is the lift coefficient equation predicted from these two values here. And so this line, what we want is to find the best line that's going to go right through our data set. So the way we do that is, see, this column here is a prediction of the lift at each angle of attack, and then this next column over is the error in that lift. And so if you double click on in this cell here, you see that it's comparing the lift that's predicted by this equation to the actual lift at that angle of attack that you got out of Xfoil. And so what we want to do is minimize this error that we have in this equation. This green box here is the RMS, that stands for the root mean square of the error in this column. And so if you double click here, you see that it's summing the error here, and then it's going to take the square root of that error, and that gives an RMS value. And we want to minimize that value, and when we minimize that value, then we found a line that goes as closely through this data as possible. Now you notice when I double clicked on that, and it shows what region here it's summing or using for that RMS value. You notice that it's not including all of the data. The reason for that is that this last point actually doesn't look to me like it's very linear. So lift, according to when we're at small angles, lift is fairly linear. So we're fitting a line through this data. But it looks like by the time we get up here, which is at 12 degrees, it looks like we've kind of departed from that line. And so I'm not going to include that last data point when I'm trying to come up with this lift equation. I'm only going to go to this the data point at 10 degrees angle of attack, and so this will be included in trying to come up with this equation. Now your data is likely going to look a lot different than this, and so you'll need to you can grab right here on this corner and move up or down and choose how much of your data you want to include. And that's just a judgment call on your part. How much of that data really falls in a pretty straight line and should be included in that equation to predict the lift at small angles of attack. So I'm going to just leave it right there, but you can set yours wherever you need to represent that linear lift region. Okay, so now what Excel is going to do is it's going to iterate on the zero lift angle of attack and the lift slope. It's going to try to come up with numbers that create a really nice line here. So I'm actually going to change these back from their defaults, and I'm going to put in a 5 here. So let's say that we start out with a blue line that's represented from these two values here, and obviously that doesn't go through our data. What we want Excel to do is choose numbers here that will force that blue line to go right through the data. So the way we do that is we tell Excel that we want to change these two numbers, and that Excel's goal is to minimize the value in this cell here. If that number is minimized, then that means that the error between the line and the data has been minimized, and so that's a best fit to our data. Now, when you first open Excel, if you haven't, well, the function that we're going to use to do this is called the solver, and it's already built into Excel, but it doesn't come as a natural thing that's part of Excel. You have to, it's one of their add-ins. And so on a Mac, if you come up here to Tools and then go down to Add-ins, then it's got a few add-in options, and you see mine is already checked because I use the solver add-in all the time. So anyway, mine's checked, but yours may not be. So you want to check that and then click OK, and that will add the solver add-in to your options here. And the way that we access it is to go up here to Data, and once you've added that solver add-in, then you'll have a button here that shows up for the solver. So let me show you where to do that on Windows. That's the one difference between Windows and Mac, is how to add in that solver. So I'm going to open this in Windows. So I'm running Excel 2016 on Windows 10, and so you see I opened up this spreadsheet. Looks just the same. Let me zoom out here a little bit so you can see a little more of it. And the way that we get the solver add-in on Windows is under File, go down to Options, and then Add-ins. And then it says Manage Excel Add-ins, and so click Go down here, and that pops up these add-ins that are possible. So I haven't run the add-in on Windows yet, so that's not checked. So I'm going to click on that. That checks it, solver add-in. Click OK, and so it takes a second, it adds it in, and now when I click this Data tab, I'll see that solver option pop up here on the end. Okay, so I'm going to continue using the Mac, but everything else should be identical. It's just how to get that solver in there that's a little different on Windows. Okay, So here we are. So I'm going to click on that solver button, and it pops up with these options. Now, it just so happened that this cell was selected when I clicked that solver button, and so it's going to automatically put that cell in this first slot here, which is exactly what we want. The objective is to minimize the value inside this cell. So if that's not the case, then so if that's blank for you, then when that's selected, just come over here and click that cell, and it fills in the address of that cell there. And what we want to do is minimize it. Now we can maximize it, we can minimize it, we can say we want it to be really close to a certain value, but what we want to do here is minimize because it's the RMS error. So we're going to minimize, and then we say by changing which cells. So yours probably won't have anything there. And what we want to do is change these two cells. So I'm going to click and drag across there. So it's going to select both of those cells. And it puts in F30 and G30. And we don't need to add any constraints. A lot of times this box is automatically checked as a default. I usually uncheck that because anyway, it probably doesn't apply in this situation, but for some of the simulations I run, that needs to be unchecked. And so everything else is pretty much good. We can accept the defaults on that. And so I'm just going to click on Solve. And you see down here, at least on the Mac, it shows you, it's already done, but down here it will show you how it's iterating through and trying to find a solution. And then it gives you the option to either keep the solver solution or to restore the defaults. And I usually just keep it even before I check them. But you can check the solution before you decide to keep it. So I'm going to keep it and click OK. And so now you can see it came up with these values here. Zero lift angle of attack of minus 2.1 degrees, a lift slope of really close to 6.2, and it automatically plugged these numbers in here. And so you see when I plug those numbers in that this blue line now passes straight through that data. So I've minimized the error between that line and the data. And so that basically says that this line is a good representation of that data. Okay, so that, one more thing we want to do with lift before we leave is choose a CL max. So from our data, and a lot of times you'll probably have data that even shows you the maximum lift coefficient here and then drops off. From that, you want to just estimate what your maximum lift coefficient is going to be. So MachUp needs that in order to predict stall. So from this data, I'm saying that maximum lift coefficient is about 1.4, so I'm going to put that in there. And then this gray box, that's grayed out because we don't need to change it. All it's telling us is that zero lift coefficient that it calculated in degrees. This is the value in radians. Okay, so we're done with lift. We have solved for these two values. The yellow values are what MachUp needs. Those are the important values that we have to solve for each of these data sets. So we're done with the lift. Now we move on to the drag. The drag is very similar, except that it has three different values that it's trying to solve for, because it's going to try to fit a parabola. Drag is often parabolic, near 0 degrees angle of attack, and so we're going to try to fit this parabola. These are the three parameters that define this parabola for this drag, for the drag behavior here. So again, the black dots represent the raw data that I have sitting over here. Now if you've added lines, by the way, then you'll need to click and drag down on this and make sure you're plotting all of that data so you can see it. And then the blue line here again is plotting drag as predicted by this equation that's defined from these three variables here. And again, this column here is the error between the two. So it's the difference between the drag predicted by the equation and the actual drag that we have from Xfoil. And again, what we want to do is minimize the root mean squared of that error. So I'm just going to set these back to 0 so we can see this guy at work again. And so we'll say that's, if we put in zeros for all of those, you can see that we just get a straight line down here. That's a very poor representation of what the drag looks like. And we'll just walk through this again. I'm going to select that cell, click on Solver, and it didn't automatically populate here, so I'm going to highlight that and reselect that cell, and now it fills it in. K27 is what we're trying to minimize. We want it to be set to minimize there, and then the cells that we want to change to minimize that, you can see if I click in there, this is still referencing these two cells over here. So I'm going to delete those out and select these 3 cells here. That's what we want to change to minimize, and then just click solve. And now you can see setting up problem. It's going to run through, and there it's come up with a solution. So click OK, and there we go. Now we have a curve that is the best of its ability has fit through that data. Now one thing I skipped over here is if we double click in the RMS cell here, you can see that again I'm only modeling that linear data. So generally speaking, whatever range you use here for the lift that shows this general linear range in the lift, that's generally the same range that you probably want to use over here to show the drag, because the drag is parabolic with lift or angle of attack. So we want to make sure that we're only trying to model the drag in that region where the lift is linear. So that's why this is the data that's selected here to minimize, or for that root mean square to be calculated from. Okay, and then we're just going to do the exact same thing on the moment estimation. So we've finished evaluating the drag coefficients down there, and then this is the exact same thing for the moment. So here's the moment as evaluated from the equation. This is the error, and here's the RMS value. And again, a double click on that. I'm only going to use the data that I used originally in that linear lift region, and so I'm going to stop and not use that final point down there. And this time through, we're trying to minimize or to change these 2 values here that are yellow to minimize the RMS there. So I'll change those back to 0, and click on the solver. And this time we're trying to minimize this RMS value subject to changing these cells here. And so I can just point out here the RMS, with those set to 0, notice that the RMS is 0.16. And now when I solve this, hopefully that RMS is going to get smaller, which means that it's getting closer to that solution. So we're going to click OK and keep that. And you see the RMS is 0.0158. So by an order of magnitude, it decreased the root mean square of that equation by an order of magnitude. Now here's a plot of the moment data. Again, the dots are the raw data. The blue line is the predicted line from these coefficients here. And you can see that this moment doesn't really follow a straight line really, and that's a challenge. I've had a hard time sometimes getting credible moment data out of Xfoil. Sometimes that's for some reason I get these step changes as I cross 0 degrees angle of attack. I'm not sure what causes that, and so I usually just run with this just as it is here and hope that the errors that I'm getting are not too significant in my simulation. There are other ways to predict moment coefficients. So if you go to full CFD, or if you're going to use a panel code, or Joukowsky airfoils have a closed form solution for pitching moment, and those are generally smooth. But for some reason, when I run a viscous airfoil in Xfoil, a lot of times I get this kind of weird behavior of the moment coefficient, and I'm not sure what's causing that. So, but anyway, MachUp models a moment with a predicting that it's just a line here, and so we have to fit a line to the data that we get out of Xfoil. So this is the line that minimizes the root mean squared error of this data, and so that's what we're going to use in MachUp. So what's happened here is we've solved now for all of these values in yellow. We chose a CL max value, and as we were changing these values, Excel was also updating this block over here. And this is the block of code now that needs to go into MachUp in order to define all of these, all of the parameters, or the aerodynamic parameters of this airfoil. So if you open a MachUp input file, you'll see that you have this airfoil. So here's the name of the airfoil, and you can fill that in. So this was a 2410 apparently, the data that was run here, but you can just change the name of it here. So let's change it to a NACA 4412. And so there's the name of the airfoil, and then it has these properties. We're going to model this with a linear data set here. Alpha lift knot in radians, the lift slope per radian, the pitching moment at 0 lift, the moment slope, and then these three are the three drag coefficients that we solve for here, and then the maximum lift coefficient there, and then there's this comment that all angles are and slopes are in radians or per radian. So we can just highlight this block here and copy that and paste it directly into our MachUp input file. Or if you're using the web version of MachUp, these are the values that you can enter directly in that Airfoil. When it asks for Airfoil information, these are the values that should just go directly in there. And so you can just copy those in, and now MachUp will be modeling as best as it can the properties of your Airfoil that you got out of Xfoil. So I hope that's been helpful. Feel free to reach out to us if you have any questions, and best of luck. Thanks.